So taking a look at this first example, we need to get a toolbar up. There we go. All right, so this very first example, we want to go ahead and first list out what is the degree of this polynomial. This is a fourth degree polynomial, which means our degree is even. Our lead coefficient is 1, but more importantly, that means it is positive. So with an even degree polynomial with a positive lead coefficient, that means my end behavior will be rising to the left, rising to the right. Take a look at the second example. The degree of this polynomial is probably the trickiest part. Now, we don't want you to actually multiply everything out here. That would be very time consuming. But what we can go ahead and do is add all of those powers. So I have a third degree plus a second degree plus a first degree. So that means the degree of this polynomial is actually 6, which is also even. The lead coefficient in this example is -4, the negative being the part that we want to focus on. So if I have an even degree with a negative lead coefficient, my end behavior falls to the left, falls to the right. And I'm perfectly fine with you just drawing arrows to show that end behavior. If you prefer to write it, that's fine also. Let's take a look at this last example. Same idea when we're looking for the degree. I have a third degree out front, I have a first degree, and another first degree. So in total, this is a fifth degree polynomial, meaning it is odd. The lead coefficient in this case is 2, but again, more importantly, we're looking at the fact that it is positive. So anytime I have an odd degree polynomial, I always like to think of my x cubed function, picture what that looks like in your mind, and that's going to help you get that end behavior. We are going to fall to the left and rise to the right. The next piece that we want to talk about to help us figure out a clear picture of what these graphs look like are the zeros of the polynomial function. So if f is a polynomial function, then the values of x for which f of x is equal to 0 are what we call, not surprisingly, the zeros. These values of x are the roots or solutions of the polynomial equation f of x equals 0. In other words, these are the x-intercepts that we're looking for. And this is going to be really important. We will be switching between the terms zeros, roots, solutions, and x-intercepts throughout the remainder of the school year. So make sure that you're comfortable with all 4 of those terms. They all mean the same thing. So we're going to take a look at this first example. F of x equals x cubed plus 2x squared minus 4x minus 8. So for starters, just a quick little note, that -8 is actually going to be our y-intercept. We're going to be talking about y-intercepts a little bit later on, but that's just an important thing to recognize. Remember that if we have 4 terms, we want to think about factoring by grouping. Maybe make a note of that as we go along. So remember, in order to factor by grouping, I've got x cubed plus 2x squared minus 4x minus 8, and we're going to set it equal to 0 now. So the way we factor by grouping, you group the first 2 terms, you group the second 2 terms, including that middle sign. That's important. We're always going to want to factor that out. And now we're looking for the GCF of each factor. So in this first one, the GCF is x squared That leaves me with an x plus 2. In the second group, I'm going to factor out a negative 4, which leaves me with x plus 2. So remember, we're looking for these binomials to match up. They're not being multiplied by each other, so we only write them once. The GCFs get combined into their own binomial, and then we write that shared binomial once. Take a look at this x squared minus 4. That is a difference of perfect squares, so we are going to factor that further into x plus 2 and x minus 2. And then we have that additional x plus 2. So if you take a look, I've got the same binomial here. So to clean up how we write these, we're going to write this as x plus 2 quantity squared times x minus 2. So what that means is that my zeros, I'm going to be looking at x equals negative 2, but maybe make a note, this is what we would call a double root. It has that power of 2 on it, which means that it actually counts for 2. My other x value, my other 0, is going to be positive 2. So in looking at this function, we've talked about the fundamental theorem of algebra before that says if it is a second degree polynomial, there are 2 solutions. If it is a third degree polynomial, there are 3 solutions. Even though I only have 2 zeros written, this is actually negative 2 counts for 2 of my 3 solutions. So we might only see 2, but we know that really there are 3 there. So let's go ahead and take this one step further and talk about multiplicities of x-intercepts. So if R is a 0 of even multiplicity, then the graph actually touches the x-axis and turns around at R. Sometimes we refer to this as a bounce. If R is a 0 of odd multiplicity, then the graph crosses the x-axis at that point. In our last example, where we had x plus 2 squared, that is what we would consider an even multiplicity because of the power up here on the factor itself. This is actually why our graph would touch at negative 2 and then turn around and bounce back off, and it counts as a double root. In that last example, the other factor, x minus 2, since it's just a single x and there's no other power, that's an implied 1, that would be considered an odd multiplicity. And that would tell us that our graph would actually cross through at that x-intercept. So, quick note here. Regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. Meaning, if I have something like x plus 1 cubed, rather than my graph at negative 1 crossing straight through, I might actually see something that looks a little bit more like this, where my graph is going to slow down, flatten out, and then cross through. It's a really subtle difference, but it's something that we should keep in mind. So this example says find the zeros and now give the multiplicity of at each 0. And then what we want to do is state whether our graph is going to cross or touch at each of those values. So taking a look here, we don't need to worry about the negative 4 because there is no variable associated with it. This first factor, I'm going to think about setting that equal to 0 and solving for x. So I think we can all see that if I were to take the square root here, square root of 0 is still 0. That means that I actually have a 0 at negative 1/2. So over here, negative 1/2. Writing that as an ordered pair would look like negative 1/2, 0. This has a multiplicity of 2, which actually means it is going to touch and bounce back off at that point. My second 0 is a little bit more obvious. We're going to be at x equals 5, which I could think about writing as the ordered pair 5, 0. This one now has a multiplicity of 3, which means it will cross, but it is going to slow down a little bit and get a little bit flatter as we approach it. So kind of thinking about what this looks like visually, this is actually a 5th degree polynomial. The lead coefficient is negative, so my end behavior is going to be up and then down. And if we just start to build up an idea of what something like this might look like, there's my x-intercept at 5. I like to put a little c next to it as a reminder that it's going to cross. And we'll call this negative 1/2, and I'm going to put a little t next to it as a reminder that it would touch. And since my end behavior starts up here and ends down here, there's only going to be one way for us to connect these dots, and that's what we're going to work up to. But we can start to get an idea of what this might look like. Let's go ahead and take a look at a few more of these examples to finish this off. In this one, notice that we have a degree of 4. The lead coefficient is negative, so we know that our end behavior is going to be down and down. In this case, I only have 3 terms. I want to think about factoring out a GCF to begin. So the GCF here, I don't want to be working with a negative out front, so I'm going to actually factor out a negative x squared, and that is going to leave us with x squared minus 4x plus 4. From here, I can further factor this trinomial, get my 2 binomials set up. Both my sides are going to be the same. This front one tells me they're both negative. And factors of 4 that add to 4, 2 and 2, which means I can go ahead and combine this into x minus 2 quantity squared. So in thinking about our zeros, this first one gives me a 0 at 0. That's going to be right at the origin. This has a multiplicity of 2, which means that it touches, turns around, and bounces back off at that point. My second 0 is at positive 2, but notice that it has a multiplicity of 2 as well. So I am touching at both of these intercepts. This is a 4th degree polynomial, which means we should have 4 solutions, and in this case, each of my solutions counts for 2. One more example here. The degree of this last one is 3. Lead coefficient is positive, so my end behavior is going to be down on the left, up on the right. We are back to 4 terms here, so we are going to factor by grouping. My first group, I can factor out an x squared, and my second group, I can factor out a negative 1, which means x squared minus 1 times x plus 3. We have another difference of perfect squares here, so I can write that as x plus 1 times x minus 1 times x plus 3. So taking a look at these zeros, x equals negative 1, x equals positive 1, and x equals negative 3. And what I want you to notice, they all have a multiplicity of 1, which means they all cross